Awesome. So welcome to Migrating 40 Gigabit Ethernet. Who am I? Alexander Graf. I work for SUSE. You might have seen me in earlier KVM forums. You might have seen me in doing random weird things. This time around, it's going to be trying to make super fast network work with KVM. So let's first, if you say migratable 40 Gigabit Ethernet, that's a lot of different words in there. Let's take a look at what migratable actually means. Live migration, I guess most of you guys actually know what it is, but let's just do a really quick recap on what it means. It basically just means we have a virtual machine on one side that we want to somehow get to another host, to basically go and take it into another container for a virtual machine, which means we serialize the state of that machine. We take all of it into a file, move it over, and there you go. You have two copies of the same virtual machine running, which means we can kill the first, and off we go. We are now running somewhere else. Live migration, really easy thing. Until you bring network into the game. So when you do network with live migration, it basically means you have to have a network card in both of those machines that is connected to the exact same physical network. Whatever physical means, it can just be another virtual on virtual on virtual layer, but they have to have the same view of the network. 40 gigabits. So who of you has a 40 gigabit network card? Well, that's a lot more than I expected. They're not really that common. We're basically slowly seeing things ramp up. If you look at the history of things, we're now roughly around 2015. You will see standardization for 40 gigabit, 40 base T Ethernet, which basically marks the standing point when things become more commodity next year, hopefully. But you can already get 40 gigabit adapters for quite a while. They've been around since 2008 or so as early hardware. It's just that it hasn't really become a commodity in the data centers anywhere, really. You use them for connecting switches, but you don't use them that often to connect machines. So let's just assume everybody of you has two of those, because just one is not enough. There's two of those, and you're trying to run awesome best benchmarks on them. If you take a current 4.2 kernel and you just run netperf, you can basically see you get a really nice curve there on what your throughput looks like. This also tells you that you will never get 40 gigabits if you do really small packets, but once you get up to 4 kilobytes, 2 to 4 kilobyte packet size, you can actually go and show 40 gigabit of data through your channels. Just pretty impressive. And now you also want to do all of that in the virtual machine. Easy, huh? Well, what do you do? First thing is you try and run virt.io. And if I say virt.io, I do mean virt.io and vhost. I'm not even going to start talking about virt.io with any vhost. If you've seen how virt.io works without them, refer to the last couple of years. We've been working really, really heavily on those. So what does vhost do? You take a look. You see this network card in the virtual machine there? That's what virt.io refers to. So this network card basically exposes a couple of rings, transmit rings, receive rings, and an admin ring to your virtual machine that the virtual machine can use to then send data, receive data, and do control administrative stuff. But we also have our real hardware that all of this somehow needs to get mapped to. At the end, virt.io is a virtual adapter that the VM sees, but real hardware does look different. So we need some conversion layer in between. And how do we convert? Well, for the rings, we have VHost net, which converts everything for us. Let's just treat it as a black box for now. And then we have QEMU that takes care of the admin ring. So anything that's control level, QEMU just does. QEMU shows whatever it was configured on over to layers on the outside. And the admin ring for the real network adapter, that's all handled by Linux, which is that's stuff we don't care about right now. The TX and RX ranks are basically handled by vhost. Well, it's more than just vhost, but let's get to that one now. So vhost, what does this really mean if we just have this gray box that says, ooh, we're handling network packets? Well, it means there is a VHost driver in this whole blob that says, I can read and write VirtIO queues. Just basically, it knows what the protocol looks like, it knows what the format looks like, so it can interpret what your packets look like. And then when you send a packet, that packet gets sent over to the Linux tap driver and onto the Linux bridge driver, and finally reaches the Linux network adapter driver, which then can send this packet out to the transmission ring. For receiving packets, the same thing happens, just the reverse. So you can see there's quite a lot of layers involved, and who would assume that we can actually manage to get 40 gigabits on that setup? Very good. We can't. We're basically capping at 20 gigabits, at least in my measurements. Maybe somebody who's more skilled in tweaking things can get further. Even to get the 40 gigs, I had to basically disable anything NUMA on that system, because as soon as you're crossing to another node, your latencies and your memory performance would just completely plummet the benchmarks to 26 gigabits. With a normal current vHost setup that you would usually have, you don't get 40 gigabits, unfortunately. Now, there's something really cool that people invented recently, which is you see those rings. There's only one ring on each picture, right? Well, but your hardware actually has multiple of those rings, so it can distribute the load between different queues. Well, VirtIO actually grew support for those ones too. So maybe if we just enable multiple queues, we can distribute between different multiple CPUs, and we can reach 40 gigabits. Yeah, almost. Didn't quite work out. You get a lot better latency if you do this, but performance, throughput is still going to be about the same. Probably because I'm just running a single TCP stream, which doesn't get multi-queued properly. I have no idea. You can also accelerate things more. So I just talked to Michael about this end of last week. You can have some special setup with your bridge, which is really, really recent, but that requires VLAN support, and it didn't have VLAN support in my kernel built in. And either way, the only thing this does is a disable promiscuous mode, which is something that I don't care about, because I really only have 2 machines connected with a direct cable between each other. So I don't have additional packets that would get filtered out. Any packet that arrives is a packet I care about. So it really shouldn't really make a big difference. But maybe there are ways to improve. There's also alternatives to the bridge thing. So you can use OpenVSwitch, which is another user-space component that you use or I don't know, honestly. Rocker is a kernel part that does jitting for that. MakeVTap, you can use MakeVTap instead of a normal tapping code. If somebody wants to go and benchmark those, I'm more than happy to even help them out, donate hardware. No, I don't have hardware to donate. Help them out, really, on how to get this benchmark. But my take on this is I don't think any of those approaches are going to be significantly faster. The bridging, tapping code is actually known as being the best we have out there right now. So if you really want to get bare metal performance, the easiest path to get there is to use direct assignment of devices. And if we want to say that, we basically say VFIO. That's the way we do it today, to assign a device from a guest from hardware into a guest. So what does it look like? Well, it means we have hardware in our host. We have lots of different PCI cards there, right? You see those? And we just take one and expose it in the guest. And they're saying those two together, like the same thing. So if you take this in queues and rings, it basically means your guest NIC and the real NIC are the same thing. They just merge, no difference. Exactly the same hardware. However, now you're trying to live migrate that piece of hardware. Have you ever tried to, while you're live migrating a virtual machine, to take a PCI card out from one machine and plug into another and preserve all of its state? It gets really hard, right? You're tied to that one machine that you just really, that's where your PCI card is in. But at least we can see some performance numbers on that one machine. And as you can see, VFIO actually performs pretty well. The one curve I left out, you can see this in the slides when you download later on. One curve that I left out is the VF slide, the VF curve. The thing I'm passing through into the guest here is a virtual function device rather than a physical function device. The blue curve, the dark blue, is a physical function, and VFIO basically performs about the same as a virtual function device, even if you use it in the host. So we're getting pretty good performance. However, VFIO is a generic driver. It means it's not even trying, it's not even attempting to make us do anything hardware specific. It just knows what a generic PCI device needs to have to see it in the guest, and it handles any and every PCI device out there, which is its whole purpose. But how about we break that mantra? What happens if instead of having one driver for every single piece of hardware that's out there, we create a subclass that only handles a single one of them? Sounds like a novel idea. Well, it means we still have all of our rings bundled by, or the same as the hardware for starters, but now we have the chance to do tunings and specific things that are very deep down into hardware details for this one particular adapter, which maybe enables us to get migration working. So let's see whether that works. Let's take a first look at the admin ring. So the admin ring is basically is just a queue that allows you to send packets back and forth to the physical function that are like saying, please set this MAC address. This is where my queues are. There are a few administrative things. It's a very slow pathy thing. So basically you have about one command per second on that thing, which is to gather statistics. But most of the time you don't care about the speed of that queue at all. However, all the data in that queue is write once and forget about it. So once you told the physical function, set this MAC address, there's no way for you to ever ask the physical function, please tell me all my MAC addresses. So if we ever want to migrate to another machine, we have to replay those commands, which means we need to record them. Well, how do we record commands? It's very simple. It's what we always do in QEMU. We add QEMU in between. So we create another admin ring, an admin queue, and admin processing layer inside of QEMU that the guest talks to, and then we have the real admin ring that QEMU now can talk to, and every command that the guest sends over, we just filter and record the ones we need. That's a very simple approach to it. The cool thing is that we can now actually save all of that state in the migration file, so all of the admin stuff is done, handled, good. Only leaves the rings. That's all the state we have, really. Well, the problem is rings are, or not the problem, the cool thing is rings are actually residing in memory. And we're already migrating memory, so it sure does work, right? Well, if the world was only that easy. Wait, what was the difference there? Oh yeah, there we go. We migrate memory, so it just work. Okay, let's take an example on the RX ring, because that's the most complicated one. How does this ring actually look like? We need to dive into the details of the hardware a bit to understand where the issues are. So what does such a ring look like? A ring really is just a physically contiguous piece of memory somewhere that basically contains a couple of entries for slots that you can write packets to. And it has a head and a tail pointer, which basically means the head is where the queue starts and the tail is where the queue ends. So the first entry is the head and the last entry is the tail. Easy. Now the problem is that both the head and the tail are part of hidden state in the in the card. So yes, you can write the tail. When you read the tail, you get a bogus value on the I40 EVF, and you can't even access the head at all. It's completely hidden. You don't see it. You can't read or write it. So we need to be, well, we can't really migrate that code over, because on the receiving end, we basically now have our queues, but we don't know how to use them because we don't know where the head and the tail is, so we don't know where to put the next packet in. It's very easy to solve, though. Well, also we can set the head, because the head is always at 0 after we boot up the card, and since we cannot set the head, we have to have the queue always start at 0. But it's very easy to solve. We have a queue at the receiving end. It has a lot of packets in there, a lot of packet slots that we could write packets to, but we have no idea which one is which. We don't know where the 0 is, where the 1 is. But what about we just mark all of them as there's a 0-byte packet that just arrived? All right. Now the guest will go in and say, sure, awesome, I found a 0-byte packet. Let me make this one slot that you just had made use of. Let me free this up so you can write a new packet into it. It will do this a couple times until we hit the first packet. So now we actually have a, oh, wait, that was one too much. There you go. Now we have a queue where we have, which starts at item 0, which is exactly what we need because that's what hardware expects. But we have a few items in between which we destroyed because we said, please, we said there are 0-byte packets arriving. So we have to write this, the queue again, mark every item as 0 again. The guest goes in, writes the head properly, clears everything fine, and eventually, after we've done this 2 times, ooh, look at that. We have a queue that starts at the first address, that ends at the last address, which is exactly what the hardware expects us to look like. And we can just pass this into real hardware, and we don't care about the fact that we're not able to read the head and the tail. So either hardware allows us to read those, or we just have to work around it. But it definitely, you can even work with it even though hardware is not designed to allow you to. It's not designed for this migration thing in mind. So DMA. It's a complicated story. If you have a CPU that's trying to write something into RAM, and your queue is just part of RAM, right? If the CPU wants to write anything into RAM, it writes into it, and KVM can trap on it and knows, all right, we have new data here, so this page is dirty. When those pointers, those queue items only point to random addresses in our RAM, which means we don't ever know where, or we do know where the packets could potentially land in the receive queue, but we don't necessarily know because the guest could be writing packets really, really fast. So when hardware now goes in and tries to and receives a packet, this hardware will write to the pointer that was pointed at by the queue and to the queue notifying the guest, look, there's a new packet coming in. However, that breaks migration. If you already know why it does break migration, congratulations. It breaks migration because the CPU, when the CPU writes data and marks it as dirty, that's what we call it, then KVM knows, all right, I need to migrate this over. So QEMU can just go and send that page over to the new machine, to the secondary machine, which means they're both in sync. Everything looks the same. Great. When we start the second machine, it runs on. However, when you do DMA from a device, we do not get that notification. So the device sends the page, writes into memory, but we do not know that it's dirty. The second machine, the receiving end, doesn't know that it needs to get updated. It has invalid data in there, so we have a non-synchronized state where both ends basically run with different contents in memory, which is something we really do not want to have. But also that one is solvable. You can either, of course, improve hardware, or you just do it in software. So how about instead of having this ring shared during migration, we again filter it through QEMU. Woo. So that way, we basically create a shadow copy of our ring, of our receival ring, and anytime we have the network adapter writing a packet, it writes directly into RAM, yes, but we do not care all that much that it writes into RAM because the guest doesn't know that anything got changed. So even though we're migrating at that specific point in time, nothing bad could happen because the guest just gave up the memory anyways. But it also writes into our own version of the queue, which means now QEMU can copy that part over, at the same time dirty the memory that was accessed, and we do know that everything's in sync and that we can migrate that data over to the new machine now. Problem solved. So what does that look like? I mean, it sounds like a lot of overhead, right? We have to process every single packet in QEMU. We have to route interrupts to QEMU to look at all those packets that came in. Turns out performance isn't actually too bad. I'm pretty sure the spike to the bottom there is just a bug in my code. But in most cases, we are really, really, really close to native I40EVF operation, which means during normal operation, you get the exact same performance as the bright blue line And during migration, you get the performance of the purple line. In both cases, you're basically better off than with vhost. However, there's obviously also downsides to it, right? You do get live migration with this approach, but you do not get memory overcommit because the hardware could write to any point in memory at any point in time. There's solutions to that in hardware, there's solutions to that in software, not going down to those. However, performance is identical to VFO in a normal operation, and at least on the throughput, we're getting very, very close to native during the migration phase too, which is awesome. But there's more than throughput. There's latency too. So you would expect that latency gets pretty bad when you do everything through QEMU. Well, let's take a look at all the latency numbers here. So native is obviously always good, right? Whenever we do a native operation, we always are pretty fast. What does cold and warm mean? Cold means I have an idle machine and I have a packet coming in. Warm means I have a machine that's running a benchmark right now and have a packet, just a ping, coming in and see how long it takes to reply. So as you can see, native is always good. Why VFIO is faster when you're warm, I don't know. It's probably just a benchmark hiccup. But the interesting parts are the vhost net and the tracking VFIO part. So the vhost net cases with multi-queue 4, because if you don't do multi-queue, those bars probably wouldn't even fit in. I got 5 milliseconds, 10 milliseconds, whatever latencies. So you definitely do want to use multi-queue if you're using vhost net. But if you're using vhost net, you're getting okay, pretty good numbers on cold, but you're getting pretty bad numbers on warm. And it was very hard. I couldn't do standard deviation on that graph, unfortunately, but vhost was spiking throughout. You basically got anything from 0.2 to 2 milliseconds, somewhere in between. Whereas with the tracking thing, it always stuck at 0.3 milliseconds, which is probably the overhead that you have to go through to get to QEMU, get the interrupt in, and inject the QEMU back into the guest. But that's not the only thing we can do. I mean, there's definitely a lot more room for improvement to get fast networking. Right? We can, for example, do hardware-aware vhost. Let's just quickly walk through these. Hardware vhost just basically means instead of going through all these layers, what if you just dedicate a VF to your specific vhost and just have them talk directly? You could even have improvements in the NIC driver in, say, an I40E VF NIC driver on the host that would allow you to pass that adapter directly into vhost. They would talk to each other. vhost would say, hey, I have a new receivable item thing, convert it into whatever the hardware thinks packets should go to, and you could directly write packets into the guest too. I haven't been able to prototype it. If anybody wants to beat me to it, I'd be more than happy to see their code. You could also go and do this in VirtIO itself. You could say, what if my guest actually knows what the queue format looks like for, say, an I40 EVF or a Mellanox or whatever adapter? So instead of just putting in, getting it VirtIO rings, you also give it real hardware rings, which it can then use if it has support for them. If it doesn't, it doesn't. It's going to be slower. With this, you basically get a new bar for the new rings, but then you have direct access to hardware queues, which means you can be faster if you have acceleration support for them. Or you could do something very nasty and fancy, which is something that I stole from VMware as an idea. What if you have just not only your VM, but you extend it and you throw in addition to the BIOS, you put in your translation code into the virtual machine? You could do it in SMM, maybe. That would be really nasty. But you could also just make it calls from the operating system. The operating system would call into something ACPI-ish, some one-time services that allow it to convert from the real queues into VirtIO queues, and then it would read VirtIO queues in again. That would mean that you basically have a direct conversion path from the rings into what the guest would want to see as the ring. The guest would not be modified for new devices, and you could even do live migration because you would just have to swap out that translation code. But yes, it's fragile, I agree, and it's a lot of work. However, the really cool benefit of it is the fast IIQ path. So you have Newer hardware comes up with mechanisms so you can directly post an interrupt into hardware into a guest while the guest is running. If your conversion code is actually part of the guest, it means it gets the interrupt straight on, and you don't have to exit the guest at all. You're also obviously running a lot less code in the host kernel, which is always a good thing. And then if you take the same idea, but instead of doing the translation in the guest, you do it in QEMU, you would have most of the benefits still. You saw the slides earlier that the latency wasn't all too bad when we go through QEMU to process the rings. If we just make use of that fact and try to implement a VFIO, an I40 EVF driver in QEMU that directly converts everything into VF queues, maybe that's fast. Interestingly enough, people are working on this already. So we had, just yesterday, I came across people who were doing OpenVSwitch with DPDK and VHost user, which essentially is that just without QEMU. So where are we? VirtIO is pretty fast. It's actually good enough if you're only running on 10 gigabits, like legacy stuff. It's all good. You're fast enough. You don't really need to do all these fancy tricks. But once we're getting to 40 gigabits or 100 gigabits pretty soon, that's going to bite you. We do have to work on something. And live migration is really, really, really what we need. With this approach, you can do live migration with a physical adapter. It's slightly hacky, it's hardware specific, but at least you have something to base on, you have something to take a look at. If you want to, you can grab that URL down there. That's where my proof of concept code lies. It's not the prettiest right now. It's not 100% stable, but you can at least see, get inspired, and check out what you can take from there. And I'm more than happy to talk to you if you have a specific device that you need to care about. So with that, any questions? Michael? Or well, actually, just walk to the microphone and then you queue there.
I have a really simple question, so I can go first. What about the transmission ring? How do you recover it on the other side?
I can barely hear what you're saying.
How do you recover the transmission ring on the other side?
How do you convert the transmission ring? We don't really have to care about the transmission ring that much because hardware marks every send packet as invalidated. So even though I do not know the head of my transmission ring, hardware will just go through the queue, see, oh, there was no packet, all invalidated until the point where the first packet that you're injecting actually comes in.
So I guess the guest could do nasty or buggy things that can cause a difference, but in practice it's not a problem?
The guest would see it, but it doesn't care.
Okay. I have a question about your first method with the writes to memory for DMA. Could you just not track anything and wait till downtime and just always copy that memory over, ensuring that you have the latest data?
Okay. Could I just track what?
Let me try again. So when you track the memory for DMA, could you instead not do that at all, but just simply during the downtime for migration, blindly copy that memory over again so you know you have the latest information?
At that point, you do not know which memory was there because the queue already got overwritten by the hardware.
Okay.
So you do not know which pages contain. So the guest keeps a copy of all the pages it wants to see packets in, and then you write those in the queue, and the queue contains those pointers. But as soon as the packet receival succeeded, that queue item gets overwritten. So QEMU doesn't know the link anymore. So you don't know what to dirty. So you'd have to dirty every memory, and at that point you can as well screw all of the dynamic memory migration.
Okay. Just one other quick comment. It seems like more and more installations of virtualization are using a fairly advanced switch in the host. And so bypassing something like a bridge or whatever that is becoming less and less practical. I mean, it would be awesome to not have to do that, but software-defined networking is getting so complicated and so advanced that we have to have that there. So it seems like we have to find a solution that's both fast and involves some type of advanced switch.
I do agree there are two solutions to this. The first is there are hardware adapters out there that allow you to do all of these encapsulation in hardware. That's one solution, right? You just tell, so as far as I saw, the I40 VF can only do VLANs, so you can say this VF goes to this VLAN, but it can't do anything on layer 2 or layer 3. Some other adapters can. So you can actually just tell the hardware, this VF goes to this GRE whatever, so it does all of the additional packets or additional packet
Okay, thanks.
padding that you need. The other thing is, yeah, I mean, sure, if you can't directly go onto your network, you can't. But even with those switches, the approach I was referring to where you basically have a vhost user and something else on the outside that directly talks to PDK, that is your switch.
Okay, thanks.
In fact, we also got the live migration working with SRV VFs, actually. Then one of the issue was the trap with the DMA operation, right? Now, you can get the same throughput performance, but if you look at the CPU utilization, I think it should be higher, right? Did you measure CPU utilization?
That one?
Okay, good.
It didn't really make a big difference. Actually, nothing made a big difference. I have no idea. I'm probably just measuring things wrong. But for some reason, everything was always about the same memory CPU utilization. I was always, so for this network throughput thing, I was always using 2 threads, two host CPUs, basically. Even if I do multi-queue, if I do anything, it was always 2.
Okay.
I don't know.
Maybe we're using, trapping with MMIO. That's the maybe. We're using, trapping with MMIO. So we modified the device driver. When the device driver tried to set up a DMA address, we basically trap. That's our implementation.
Okay. Yeah, I have very nasty or very very special code in there that only traps on the pieces that I really care about. I don't trap on everything, but all of the registers in the I40 EVF are 4K aligned, so you can only trap on the ones you really do care about, and you only trap on the tail writes.
Okay, and also, what kind of a downtime do you have?
Same as any other mechanism you use for migration.
Which is.
Whatever speed you can actually use to, from your cutoff, whatever time it takes to transfer your memory over and resume it on the other side, it's the same.
Okay. So you didn't measure?
I didn't measure it,
okay.
But there's very, very little code running during that time. And I have another thing there that actually sends an ARP packet at the receiver end after as soon as it starts up to notify the outside world that MAC address is actually at that new port now. So you really shouldn't see any more downtime than with the usual approaches.
Okay.
All right, so we are about over time for 4 minutes now. If you have any more questions, just come over to me after this. Thanks a lot for attending, and have a nice KVM forum.